Good morning, good afternoon, or good evening. We are talking today, MSM3, about Unit 2, Lesson 8, Scientific Notation. It is called scientific notation because it is used most in science. Students will be able to identify numbers written in scientific notation. Students will also be able to convert numbers between decimal and scientific notation. So if we look at the measurements in the table, is it easy to tell whether or not something is big or small? So density of air, you can see over here, is listed at 1.61 times 10 to the negative third. Radius of a calcium atom, well, we know atoms are small, 1.97 times 10 to the negative 10th. 1 light year, 9.46 times 10 to the 12th kilometers. And the mass of a neutron, now a neutron being part of an atom, only 1.675 times 10 to the negative 24th grams. All of those things are written in what we call scientific notation. And it's a way to write very large or very small numbers without having to write out all the zeros. Can you guess which ones are the small ones? Well, the small ones have a negative exponent on the 10, where the large ones have a positive exponent. Scientific notation is always going to be in the same form. A number represented by A times 10 to an exponent. And it says that A has to be between 1 and 10. It can be 1, right? A has to be greater than or equal to 1, but it has to stay less than 10. And N, the exponent, has to be an integer, meaning the exponent has to be positive or negative, but it has to be a whole number, no decimals and no fractions in the exponent. The decimal number A will always be greater than or equal to 1, but less than 10, meaning it will always start with a single digit in front of the decimal point. You will always multiply, so you'll notice there is a dot there for multiplication, and the exponent on the power of 10 must be an integer. So you will notice that 10 is part of our format. It will always be a power of 10 to some exponent that is an integer. For example, 5.347 times 10 to the fifth. We know it's in scientific notation because 5.347 is greater than or equal to 1 but less than 10. It only has a single digit in front of the decimal point. The decimal is being multiplied, so we want to double check for multiplication, and it has a power of 10, 10 to the fifth. The exponent is an integer, that 5, no decimals, no fractions on it. Are the following numbers in scientific notation? So if we want to tell whether or not something's in scientific notation, we're basically going through that checklist. Does the first number start with only a single digit in front of the decimal point? It's between 1 and 10. Yes. Multiplication? Yes. Power of 10? Yes. And the exponent is an integer. So we would say, yes, this is in scientific notation. Second one, 7.075. We've got that single digit in front of the decimal point, so it's between 1 and 10. Multiplication, power of 10, and the exponent is an integer. Remember, it can be positive or negative. The negative integers, meaning that the number is representing something very small, whereas the top one, the positive integer for your exponent, means that the something is very large. 4.1 plus 10 to the sixth. Now, if you take any sort of standardized testing, they will often do this. It looks like scientific notation, except for the fact that it's got a plus in there. So we would say this is a no, must be multiplication. Next one, 8 times 10 to the third. So 8, is that a number between 1 and 10? Sure is. Multiplication and a power of 10, and the 3 is an exponent. So that would be a yes. 7.64, that looks good, between 1 and 10. Multiplication, 8 to the 5.2. Now we've got two different issues here. Number one, it needs to be a base of 10. So a base of 10 needed, and this one has a base of 8, so that's a problem. And exponent must be an integer. And so what's the problem with 5.2? No decimals, no fractions. So this one actually had two problems. 0. And I'll highlight them so you can see. 0.08 times 10 to the third. Well, we've got multiplication and we've got a base 10 with an exponent that is an integer. However, 0.08 is not between 1 and 10. It starts with a 0. It does not have a digit other than 0 in front of the decimal point. So this is a no. We would say 0.08, too small. Last but not least, 75.4 times 10 to the second. You probably already heard the problem there. 75.4, not between 1 and 10. So we would say no, 75.4 is too large. And on both of these, remember, it had to be between 1 and 10. Oh, I'm sorry, that should be A, not N, because we're talking about the number out of the front. A 1 is acceptable, but between 1 and 10 and including 1. All right, now if we take a look at the back, to write a number in scientific notation. So how do you create a number in scientific notation that's really large or really small? Move the decimal point in the number so that you get a number greater than or equal to 1 and less than 10. Count the number of places that you moved the decimal point. And if you moved it left, meaning you had a really large number and you moved it left, you'll have a positive exponent, like this first one. 1, 2, 3, 4, 5, 6, 7, 8. 2.57034. Don't need those extra zeros at the end. Times 10 to the 8th because I moved it 8 places. Now, if you move it to the right, because you had a very small number, 1, 2, 3 places, 2.75 times 10 to the negative third. Your exponent is negative. Now, how did I know where to stop? I stopped so that I still had one digit in front of the decimal point that was other than a 0. So 2 point, I know that's between 1 and 10. 2 point, I know that's between 1 and 10. This one's a large number. I'm going to move it to the left because it is large, 4.1269 times 10. I moved it 3 places, 10 to the third. Positive exponent because it's a large number. 1, 2, 3, 4, 5. Move it until I get just the 8 in front of the decimal point. Times 10, I moved it 5 places, and because it was such a small number, to the negative fifth. You'll notice the decimal point, if it is not written, starts at the end of the number, far right side. 1, 2, 3, 4, 5 places to the left. And because it was such a large number, 3.45 times 10 to the fifth. Same idea, decimal point starts at the end. 1, 2, 3, 4, 5 times 10 to the fourth. Small number, move it 1, 2, 3, 4 past the 4. So I have just a 4. You could put 4.0, but there's no point. 4, sorry, that's a funny joke, right? 4, no point. 4 times 10 to the 1, 2, 3, 4. I moved it 4 places, and because it was such a small number, 10 to the negative fourth. 1, 2, 3, 3.2, large number, times 10 to the third. And this one, I only have to move it 1 place, 2.696 times 10 to the first. Now, it doesn't seem like a very large number, but you can also think about that. I moved it to the left. So the first is an exponent that's positive. You can also say, well, if I multiplied 2.696 times 10, I would get 26.96. What if we're going in the opposite direction? What if something is in scientific notation and you're trying to take it back out to standard notation, which means it doesn't have the times the power of 10 anymore? So positive exponent means you need to be expecting a large number. 2.35. You're going to write 2.35 and you're going to move the decimal point 6 places. 1, 2, 3, 4, 5, 6. Now there's no digits here at the end, so it's 2, 3, 5, and all of these loops that have no number get a 0 for a placeholder, and then you go put the commas where they belong, so you can tell that it's 2,350,000. How did I know to move to the right? 6 was a positive exponent, so I knew I had to get a large number. Moving to the right gets me a large number. Next one, 4.035, 4.035. Got to move my decimal point 3 places, positive 3, so I'm expecting a large number, 4,035. Notice I'm writing a final answer with the commas in place that don't have the loops underneath. 18.42, so I'm going to write 18.42. This one has an exponent of negative 2, so I'm going to come left 2 places to make my number smaller because the exponent was negative. Now, if my exponent moves it 2 places left in front of the 1, it's going to be 0.1842. Notice again, I rewrite it. Final answer starts with a 0 point if necessary, and it has no loops underneath it. 1.3 times 10 to the negative 6. 1, 2, 3, 4, 5, 6. Way over here. 0.12345. There are 5 empty loops that are going to get zeros as placeholders, and the 1, 3. 6 times 10 to the fourth. Now 6 has a decimal point sitting after it to the far right, getting larger. 1, 2, 3, 4. This might be one that you could just do in your head and you wouldn't need the loops at all. 60,000, a 6 with 4 zeros. Last but not least, I'm going to write the 7. 10 to the negative third means it's going to get smaller. 3 places to the left. 0.2 loops that have no number get the 0 placeholders, and a 7. So positive exponents represent large numbers. Negative exponents represent small numbers, not negative numbers, just small numbers. So things that are very, very small, like things in science that have to do with the thickness of a hair or the diameter of an atom, things like that, that would be really, really small, they get your negative exponents. The idea is that you have something like, in this case, 1/1,000,000th. The positive exponents representing the really large numbers like a million. All right, if you have questions, see you in class.